Welcome to this Tagira Calico training or workshop. And today's topic will be around kube-proxy, understanding what it is doing, how we can potentially debug it, and why, of course, it is so important in Kubernetes clusters. So I also would like to welcome my colleague Jane. She's based in the UK. And myself, I'm Philip. I will be your presenter today. So if you want a photo of me, feel free. So I do have some experience in networking and load balancing, as you can see. One of my things I love to do is security. That's why I also run a few blogs which basically focus on security and container security. So feel free to get in touch through Twitter, email addresses, or LinkedIn. So let's switch to Calico. So what is Project Calico? It's one of the biggest, one of the most famous projects inside of typically Kubernetes, because Calico basically implements what is called a network CNI, a container networking interface solution, as well as a network security solution. We typically refer to it as networking for Kubernetes, but it also supports virtual machines as well as host-based workloads. So that means that you can actually implement a similar way of doing security across all your cloud-native workloads, if that is a requirement. Calico is open source, so there's a lot of input from the community that helps in maintaining Calico, together with Tagira, which is a company and founder of the project. So if you want to know more about Calico, there is a lot of information around there. So go to the projectcalico.org website, hit us on Twitter, but for sure also join the Slack channel. It's a very responsive Slack channel. There are a lot of contributors, and if you have technical questions or the type of questions, feel free to post them over there. As I said, there are a lot of people around there, also people from Tagira. So chances are you get a very fast feedback. So just to give you an idea that Calico is popular, as we know, and there are probably more, there are more than 1 million nodes today which are powered by Calico. And that's only the part we actually know. So if I sparked your attention, feel free to check it all out. There's a lot of information, very detailed information. So you should have enough things to do for the weekend. So as I mentioned, Calico is a highly scalable networking solution. There are a few different modes in which you can basically deploy Calico across your data centers, but also inside of public cloud offerings as of today. So just to give you an idea, probably if you use the cloud or if you use on-premise solutions, you have been in touch with Calico. As I said, there are two parts. One is the CNI. A lot of distributions and a few cloud offerings do implement the Calico networking solution. But most of them for sure also support what is known as Calico network security policies. In some of the standards, some it's an option, but in most, and for sure the ones here on the slide, do have support for network security policies. For example, in Azure or in Rancher, it's an option to basically enable it when you deploy your cluster. A good reason to do it, it's not really the topic of today, but Calico network security policies do offer way more granularity and flexibility than native security policies that you find in Kubernetes. Okay. So a very small recap on Kubernetes networking, because kube-proxy today is basically relying on this part. So as you might know, once you install Kubernetes, you need to define one or the other CNI. Basically, the container networking interfacing is necessary because containers need to talk to each other. They need IP addresses and so on and so forth. So one of the reasons that Calico actually developed network security policies in the past is that if you deploy Kubernetes, the network seen as from the pod side is actually one big flat network. That means that every pod can communicate with every other pod in the Kubernetes cluster without doing any type of address translation. So they should see each other's IP address. So I typically looked at it as one big network where everybody could reach everybody. And this is a little bit in contrast with what we typically want to do from a security side of things, segment things or micro-segment applications. So that's one thing. IP addresses that can reach typically anyone. The other nature of pods is that the IP addresses are ephemeral, meaning that at the end of the day, the IP address assigned to a pod in Kubernetes, you cannot rely on it. It can change, it can go away, it can come back. And there is really no way in knowing which pods, which service is using which IP address. Yeah. Last but not least, all the IP addresses that are assigned to pods are typically IP addresses coming out of a private range somewhere that resides inside of the Kubernetes cluster. Although not always, but you can have, or most of the time, the IP addresses are non-routable outside of the cluster. Very often, the IP addresses of the pods are not even seen on the networking or the physical networking on which your Kubernetes hosts reside. So the important part here is the CNI. So every Kubernetes node basically has a kubelet service running. Kubelet is the service which is running on every node that is actually pulling the Kubernetes API to see whether it should spin up a pod or not. Once kubelet decides to spin up a pod, it will ask the CNI, which is a binary which is installed, or a pod or something like that, which is running on every Kubernetes node. It will ask for an IP address and make sure the interface is connected to the pod, to the correct network, and so on and so forth. So there's a lot of things to say about how the networking works together with Calico. There are differences between the Calico modes like IP and IP, which requires BGP, as well as the non-encapsulated mode, as I mentioned, but there's also support for VXLAN. So building the tunnels in between the nodes, making sure that pods can reach each other on other nodes, that's essentially the task of the CNI, and as such Calico, together, but not necessarily also the IPAM part. The IPAM part, so the IP address management part of Calico, will make sure that the IP addresses are assigned in a scalable, routable way towards the pods. But if you want to know more about it, I mentioned the link. So feel free to catch up on that part. Today, we're going to talk about kube-proxy, which will basically be an extension of the networking capabilities. So just to show you, if we take a typical deployment, so I created a deployment, I basically told them to use an Nginx image. Important to note, although we always use it, these containers or these pods which are spun up, they will have labels. Every pod that is spun up will have a label, in this case, called up equals Nginx. It's important to note because in the next why when we discuss actually the services concept, you will see that we need this. In the deployment, you can also specify the number of replicas. The replicas typically means that, okay, spin up this deployment, and at every moment in time, I need 3 identical copies of these pods running. This is controlled in Kubernetes by what is called a replication set. So at any given time, Kubernetes, like it has a kind of self-healing mechanism, will make sure that there are 3 instances of these pods running. That would allow us to do, for example, a scale up. You can actually issue a kubectl API call asking to increase the number of replicas, for example. That could be manually, or that could be through a mechanism of auto-scaling, which is supported in Kubernetes. So for whatever reason, at a given point, we might increase the number of replicas to 5, for example. Well, once this declaration is done, Kubelet will actually see where it has to spin up new pods or not. And as such, you can spin up new pods on the selected nodes. The selection of the nodes is actually done in Kubernetes by the scheduler service, which is running on the master. So why this? You can scale up, you can scale down. As you can see, IP addresses are assigned, and from a user perspective, you cannot predict it, so they are randomly, although you see, for example, this is an example of Calico, of course, so that some nodes will have a 71 part, a 122, but that's something which is decided by Calico to make sure that we can do efficient routing in between the nodes of our cluster. So, but the IP itself basically is not known upfront. Even if they are spun up, would we be able to figure it out? Well, it would be very hard to basically configure clients to connect to these IP addresses. First of all, they're not accessible from the outside. And 2, if something happens, for example, a pod crashes or is deleted, well, the nature of Kubernetes is that Kubernetes will basically detect that we're from 5 pods to back to 4. So at that point, Kubernetes will make sure that a new pod is spin up somewhere where we have available resources. So long story short, connecting to these pods, imagine these are Nginx service on port 80, is pretty difficult if you don't know these IP addresses. So that's why Kubernetes at a given point introduced the concept of a service. A Kubernetes service, the wiki explanations and the Kubernetes explanations are more difficult than the concept itself. But basically, a Kubernetes service, and there are quite some services or types of services available, is basically a way to logically group a set of pods. So if you create a service Nginx, you can actually say behind this service Nginx, there is, for example, all the pods that make up this service. Well, that is done by a selector, and a selector basically captures a number of pods based on a label. So if I go back to this slide, that's why I need absolutely this label. Because once I create a service, all these pods, no matter how many or less, no matter if they change IP addresses, will be, let's say, hidden behind that service. This service is implemented in a few different ways, but the most common one is as a cluster IP. Meaning that if applications need to talk to these logical set of pods, they don't talk to the pods directly, but they will try to connect to the service. That means that no matter what happens in that service, the originating client or the originating application doesn't have to bother. Yeah? So that's how and why we speak when we talk about microservices, about decoupling services. That's why you can actually change a part of an application without having to develop or redesign the entire application. So services is an important part when it comes to decoupling. Another one that is relatively intriguing, I found out yesterday night while I was preparing for this, is service discovery. We don't often talk about this concept, but even if you have a service, how can a pod basically figure out to what port it needs to connect, to what IP address of the service it needs to connect? So in Kubernetes, there is also the provisioning for service discovery. There are a few ways to do it, but very often this is implemented, and for sure in the later versions by Tor DNS. So to define a service, it's pretty straightforward. We actually create a Kubernetes resource of type of service. We give it a name. Think about the name for a second, because that name will be used for service discovery. We basically say that this service catches all the pods with the label app equals nginx, and that this service is reachable on port 80. So port 80 in this case is the port number, so the TCP port number, as you can see in this case, on which we can actually connect to the services, or sorry, the pods behind it, no matter on what ports they basically run. Once you create this service, as you can see, there is no IP address definition in that service. That's actually handled by kube-proxy, the topic of the day. So once you create this, a lot of events will happen to basically make sure that this implementation is made feasible on the Kubernetes nodes. As you can guess, there is a lot of proxying or address translation that needs to take place, load balancing to make sure that this concept works. Well, this is the task of kube-proxy. Something I struggled with in my earlier days is how to reach all this. Well, every time you define a cluster IP or a cluster, a service definition, well, the name is available inside of the namespace as my nginx cluster IP in this case. But don't get mistaken, these service IP addresses or these services are accessible cross namespace. Yeah? So if you want to access this service out of another or different namespace, well, you need to address it like my nginx cluster IP dot the namespace in which it resides dot svc cluster local. Depending on where you are in which namespace, you can actually omit this. But if you want to make sure it works every time, just specify the entire name. So there are different types of cluster IPs or different types of clusters, because as you can see, this IP address, again, is a private IP address, so it's not reachable from the outside. So services cannot connect at that point. That IP address is chosen from what is called the service sider. So when you install Kubernetes, you basically have to specify the pod sider, which is basically the network range from which the IP addresses of the pods are chosen. That is managed by Calico in this case. But there is also a range of IP addresses from which these cluster IP addresses are chosen. This is known as the service sider. That's something you specify once you install Kubernetes. As long as these service IP address ranges are not used somewhere on the outside, there is no problem. They are not accessible from outside neither. So they need to be unique, or it needs to be a unique range inside of Kubernetes. Now, this is cool. This would enable us that a certain deployment can talk to this deployment without knowing the IP addresses. It can use DNS to resolve actually to this cluster IP address. The cluster IP address is something which is managed by Kubernetes and by kube-proxy. So as you can see, it's not defined here at any point. Now, to make sure that our applications are reachable from the outside, we need to slightly modify this service definition. So once we basically define the service type of NodePort, in the previous slide I omitted this, but you could basically say type cluster IP. If we would change it to type NodePort, an additional steps happen. So once you apply this NodePort service, what will actually happen is exactly the same. We'll make sure there is a service definition. There will be a cluster IP that will be listening on port 80, as I mentioned. So the idea is exactly the same, but on top of this definition, we'll also make sure that the external or the service is actually exposed on the Kubernetes node. That means that once you apply this, I can already reveal why. Iptables will make sure that on the, let's say, public-facing interface, essentially on all interfaces, so it's on the bind address, you call it, which is by default 0000, so all IP addresses of a node, will make sure that this port, in this case, 30970, so if you connect to the node on this port, the node port, you will be address translated to the cluster IP on port 80, so meaning here, which will make in turn the decision to destination net you to one or the other pod. So the main difference is here, once you specify type NodePort, that kube-proxy will make sure that on all the IP addresses of that node will actually expose a port. 30,970 is just the example and the number that came up when I did it. These port numbers are relatively random. They're always somewhere in the range 30,000 and higher. It's configurable when you install kube-proxy. But typically, that's a range of ports from which kube-proxy will choose these ports. As you can imagine, there is another problem that pops up here. How the hell do you know what this port number is? No? So it's not that easy. But to summarize, at this point, when we deploy the NodePort cluster service, our pods become reachable from externally on the node IP addresses. If your pods are distributed across multiple nodes, well, this process happens on all the nodes. That means that if you have 5 nodes, all 5 nodes will be listening on port 30,09070. Once you connect to it, once we select finally a pod, the CNI will make sure that you can actually reach the pods. Now, this is all cool, but it's not really flexible. As I said, the ports are higher number ports. They're not always predictable. So to solve this, we need to make a small jump outside of the Kubernetes cluster and outside of what is in our control. So there is also an option to essentially specify the type LoadBalancer as service. So type LoadBalancer is, let's say, one step further than NodePort, because it will do exactly the same, create a cluster IP address. It will expose a higher port number on every node. But on top, and here is the catch, kube-proxy will also try, or a controller in Kubernetes will also try to essentially configure a load balancer. That load balancer is not part of Kubernetes. If you didn't install it, it will not work. You could use F5 or AVI networks or Nginx or something, whatever you would like to use for that. But it means that once you define this type of load balancer, Kubernetes needs to be aware, and this is typically implemented by a vendor type controller that will talk to the load balancer and to make sure the load balancer is configured correctly. Since the title was self-managed on-premise, this means that you have to do quite some integration between your Kubernetes cluster and your load balancers to make sure that this is happening. The idea is that once the service is defined, somebody or something goes to the load balancer and tell them, if you see incoming connections on port 80, well, send them to the nodes on port 30,970 in this case. So, but it needs an integration with a load balancer. If you would basically simulate this lab, for example, in DigitalOcean or in AWS or in Azure or something like this, depending on how you set up, but typically if you use a managed cluster, this integration is already done for you. So if you copy paste this, for example, in DigitalOcean, which I did, it will automatically configure a load balancer. And after a few minutes, you actually have a load balancer. To see it in action, I already took a screenshot to make it a little bit faster, but at the end of the day, as you can see, I deploy an application. We see IP addresses which are in the pod cider. If we define the services at this moment, I already defined a load balancing service in this case. As you can see, there is what we call an external IP address. This IP address is a public IP address, which is the IP address of the load balancer inside of a cloud. If you define another service, the expensive part is that it will actually create an additional load balancer. It will get an additional IP address, as you can see. So from a cost perspective, this might be getting expensive in a cloud environment, but if it is on premise and you do have IP addresses, that might be a solution. Okay, and then automatically port 80 on the load balancer is mapped to the specific node ports connected to the correct cluster IP addresses. Okay, just keep in mind, I put a tool here. Creating a load balancer can take a few seconds up to a few minutes for sure in cloud environments. So using the load balancers has its pros and cons. It's a little bit outside of the scope for this discussion, but it's something which is used quite a lot. Another way to basically make our services accessible outside of the cluster is through what is called service advertisement over BGP. When you deploy Kubernetes on-premise, typically, you can actually configure Calico to do BGP peering with your network infrastructure, which by default is not the case. So if you explain to Calico that it can actually exchange BGP routes with top-of-rack routers or firewalls or something like that, basically your network infrastructure can be made aware of the service IPs or the service ranges that you want to essentially make available. So through BGP, you can actually announce the service side or a range of the service side or a specific IP address to the, let's say, network outside of the Kubernetes, so that connections that are coming in, from example, through a firewall can be routed to the correct nodes. That might be a great idea if you want to use that for redundancy reasons, or if you want to use ECMP, equal cost multipod, or some other kind of reason. The difference here is that accessing the nodes or the service IP addresses is handled by routing and BGP, while in the previous example, it is actually managed through the load balancer. Yeah, I think there are two camps in the world that will prefer one or the other. So how the hell, as I already said, do these nodes implement actually all these address translations? So it's difficult. You don't have to look at it honestly, but if you want to troubleshoot it or debug it, it's cool to have a hint. So the trick is that on every node, on every node of your cluster, including your masters, there is actually a pod running or a service running. It depends on how you set it up. But if you use kubeadmin, it's up to my knowledge always a pod. So on every node there is a service or pod running, which is called kube-proxy. Kube-proxy is essentially a service that polls the Kubernetes API server, who in turn will poll the etcd database. So not on the master nodes, but on the working nodes, there are actually two things running. One is kubelet, that will basically have the task to see if there are new pods to be spun up and spin them up. Kube-proxy is a second service on the working nodes that will basically poll the Kubernetes API to see if there are new services created. So if somebody creates through kubectl a service, yeah, everything is declared inside of the etcd database. Well, kube-proxy will poll the kube API to see whether it needs to create something based on the information it retrieves from the kube API server. Kube-proxy will, on the specific node, create a bunch of network rules, which are very often Iptables rules. So that's the task of kube-proxy. Yeah? If you want to figure out kube-proxy is spun up through means of a config map, you can open that config map and see how it is all configured, how it is authenticating, and so on and so forth. Nice thing to do if you want to understand the security part of kube-proxy. Kube-proxy typically supports TCP and UDP and SCTP, but to be honest, I've never seen the latter one. So that should be fine. Now, kube-proxy does need a few configuration parameters, just as Kubernetes will. So during the kubeadmin init phase, you can actually specify a few things. The higher part here is basically how to configure the cluster. So you see, you can specify the service ID, the pod subnet, and so on and so forth. But for this case, it's important to know that you can also configure kube-proxy while you're setting up Kubernetes. And the important part here is that you can basically specify a mode. By default, the mode is Iptables, and that's what's, of course, used most. But in some cases, and these are typically performance cases, you might use other mechanisms to implement these forwarding rules. So you can find all the information on how it is configured exactly in the kube-proxy config map. Feel free to reach out, but essentially it's pretty easy to do. Alternatives to Iptables are IPVS or NetNS. It's a more efficient way of doing the distribution and load balancing. It's faster. The problem is that it's not in the Linux kernels by default. So you have to look a little bit if it is supported or not. And at the end, install IPVS or not. That's something you have to do, of course, up front and change the mode. It's faster in higher node clusters, but up to 100 nodes or a few thousand services, Iptables will work fine. You might find some links to kube-proxy in user space. You can actually replace Iptables also by a user space proxy. That's technically possible. That's also how it worked in the very old days. But it's not really scaling, neither the performance. So by default, this mode is disabled. But sometimes you see it popping up. If you want to see beautiful charts and so on and so on, go to this link. I will share the presentation after on. You can actually read all about what the performance improvements, pros and cons are switching from Iptables to IPVS. If you want to go deep dive in how Iptables in this case, and this is how I set it up, is doing all this stuff, well, be prepared to become an Iptables expert. We'll do it in the live demo if we succeed, so that you can find more or less how to look at it. But after some time, you will find your way around. You will see what actually happens or doesn't happen when you apply services. Now, if you look around today on the internet, or you ask yourself the question, do I actually need kube-proxy? You'll find some links. Some vendors to replace kube-proxy by their own kube-proxy. Some of you will tell you that eBPF might be a solution forward on. That's why Calico also has an eBPF, so an extended Berkeley packet filtering data plane technology preview, which is actually a new way of doing all the redirection of packets. It's based on kind of microcode that you're running in your kernels that makes sure the packets reach the right pods. eBPF is relatively new technology. It's high promising, it's very fast. You don't have to go through Iptables, which can be slow if you have large environments. So nothing but good about eBPF. So if you want to try it out, Calico has a tech preview since version 3.13. So go and check it out. If you want, maybe we'll foresee a webinar based on how to set it up. It's pretty cool. But from a, let's say, feature or functionality perspective, the idea is exactly the same. It just allows you to scale even bigger than we scaled today. Of course, Calico, everything we discussed was about the Calico open source part. There is also Calico Enterprise, which builds on top of open source. So if you want more extensive logging, if you want to know who's talking to who, if you want to implement security policies on services or on pods and have visibility, Tagira or Calico Enterprise is the way forward. Feel free to check it out. Also feel free to ask for a trial. So that would conclude the PowerPoint part. Maybe we have one question or two questions while I switch to the demo part.
We've got one question in the Q&A, Philippe, and it's actually moved to the answered section because I let Deepak know we'd take it in the break. Sorry for that. Let me know if you can't find it easily.
Okay, yeah, I see. I see. What's the selection criteria to roll out new pods on various nodes? The answer is I don't know, because this is actually the task of the Kubernetes scheduler. So once you actually do a scale out, in Kubernetes, you will actually tell Kubernetes that you need 5 pods. The scheduler basically calls the Kubernetes API to see whether it needs to schedule new pods. The scheduler is a very complex part in Kubernetes that will basically take into account what's the load, what's the CPU, what storage is available, do I need a specific storage type, and so on and so forth. So based on the decision of the scheduler and the available resources, the scheduler will actually tell the Kube API to spin up the pod, for example, on node 2. If the kubelet on node 2 checks the Kubernetes API, it will tell you, oops, you have to spin up a pod, and then the kubelet will do that. But the decision on where to spin up what is pure something which is based in the scheduler. You can find information on Google, but it's a pretty complex thing. Of course, you can influence it through means of selectors and node selectors and stuff like that. But it's a pretty complex task the scheduler is doing. They told me that that's also the reason why it's totally separated as a service in Kubernetes. I see a question on eBPF deployment. In eBPF deployment, if you do it, it's basically using eBPF code to do it. We can chat offline, but there are quite a lot of tools, but essentially all the redirection is done in the kernel. So we do not use Iptables or IPVS for that. So using eBPF, no one have to use different side. You don't need to, but typically when you want to announce service siders, there is a possibility in the cluster, in the service definition, to basically say a cluster IP, or sorry, an external cluster IP. So you can basically choose an IP address and announce that IP address to the outside world. Because if you would announce the 10.something address we used in the demos towards your routers, yeah, locally it might work, but from externally, but you can use a different cider. Pod ciders for the services. Pod ciders, it depends. Pod ciders, you can announce them if you want to, but it will only work without encapsulation for that matter. Okay, let me see if I can go to my Slack machine. We have some time left, so let me do this for a second. The examples or the stuff I'm going to copy paste, I'll paste it in the chat. So that's a link. This is just the demo script to save me from typing too many mistakes. So you should have received that link, and I hope you can see my screen. So let me increase the font size and clear.
Not seeing that screen yet, Philippe.
You see the green screen?
Nope.
Nope. Let me see. Share screen. Now you see my screen?
Yes.
Yes, okay. I was typing, please. Okay. So essentially, I have a Kubernetes cluster here, kubectl. Get nodes with a lot of latency at this moment. I see 3 nodes. If you look at the kubectl, that's not going to work. kubectl, let's see if we can see which pods are in the kube system. namespace, we can actually see that we have 3 times kube-proxy running. If we add the -O white, we should also see that they're running on every node of our cluster. Okay. For those who are interested, we can actually see the config map also. If you do kubectl, get config maps in kube system, we actually see that there is a config map called kube-proxy. So if you do kubectl describe config map kube-proxy in kube system, and you scroll through it, you can actually see that this is how kube-proxy is configured. As you can see, kube-proxy knows what the cluster side is. This is important because it needs to know for which clusters and which IP addresses and so on to basically do its task. And this is the IP address that you will actually using. So that's all IP addresses on which kube-proxy will expose the services. So let me clear this up again. So I made myself a while back a small microservice which I could control. So that's what you can actually see on the GitHub page. XXRadar is mine. So if you want to use the application, feel free. If you don't want to use it, also okay. But you can use any type of application or a simple Nginx for the example. So let's see if the pods. I cleaned it up before the demo. So I'm going to create the application. So as you can see, created a bunch of services, created a bunch of applications. Let's see if it is up, you see. And if everything goes right, everything is up and running. So I created about 5 Nginx deployments, and I created about 2 backend servers. But as I said, you can use anything just to have an example. Okay. So to see if everything is working well, fine, and to basically repeat what we said, if we can actually see what pods are running and show us the labels. So if you do this, maybe I'll increase it again. You see all the pods are running. You can see all the IP addresses assigned to the pods. This is coming from the pod side. As you can see, only the third byte here, or the third byte is changed depending on which node, but that's a Calico decision. Yeah. So this is managed by Calico. So you can see all the pods have labels, an app label or a run label or something like this, and also some labels related to the deployment, but let's focus on this one. Of course, you can add any arbitrary label if you want to. So these are all the pods. So if you want to repeat the exercise and you say, okay, let's scale up, for example, echo server 1 to 5, it will do it. If you go back, we'll actually see that we have 5 echo 1s. Yeah? So, and it took other IP addresses depending on which nodes it was. So pretty cool, but the idea is this is a microservice app. So the part of this application that want to connect to the echo server part, they need to have, of course, a service. So I already created the service. So let me clear this up again and maybe enlarge again if I find the plus sign. Yeah, okay. So if I want to check what services are already defined inside of the upgradable demo namespace, you can actually see that I already created a bunch of services, and that every service is basically hidden behind a cluster IP. Okay, so these cluster IPs, as you can see, they are private, so they're only reachable at this point inside of the cluster. If you want to play around with it, well, it's pretty okay, and we'll show you how to do it. So as you can see, there is a service. If you want to know how and what this service is capturing, well, you can basically ask to describe, for example, zone 6, just an example, and it will tell you that it is listening on port 80. This is the IP address of the service, as you can see, that it is listening on port 80 and on port 443. And you also see the list of endpoints. Yeah? The service itself doesn't contain the endpoints. Yeah? The service basically asks the kube API for the endpoints of that service. So the number and which pods are actually in the services is also stored in etcd. It's kube-proxy that asks for that information to code the IP table rules. Okay, but that's how you can actually figure out what's behind the service or not. So let's put a proof in the pudding to see whether or not we can actually access this. So I'm using my own container, but you can use your whatever container in which you can exec. So I'm going to spin up my hacking container with some tools. So I could basically do a curl to, so I'm inside a container in the upgradable demo namespace, but you don't have to. So I could basically say, okay, curl me this, and I get some information back. If I curl again, please note the hostname server, and it doesn't, yeah, sometimes it changes because I actually scaled it out to 5. Every time I connect to the service IP address, Iptables will choose another backend server. Okay. From the service discovery part, I could actually do, for example, zone 6. Yeah, that would work in this case, as you can see. But that's because I'm in the namespace upgradable demo. So if you want to generalize it, you can basically say, if you curl zone 6 in upgradable demo.svc.cluster local. If I didn't type any mistakes, you can actually see that it also works. So from any pod in any namespace, a pod can connect to, for example, zone 6 upgradable demo, which is basically front-ending Echo Server 1 or one of the backend pods. So this is how it essentially works. Okay, so if you want to dive deeper in how this all works, so let me exit this container and clear up my screen a little bit. So let's say the brute force way I typically use for myself is if you type iptables list and also show the net tables, and you hit it, you get bumped or DDoSed with a lot of information. I did this on purpose because in the very beginning of your iptables rules, if I can find it, you can actually see that in the pre-routing chain, for those who are familiar, that one of the first things is about Calico networking, and the second thing that is invoked is kube services. So that means that once packets come into the Linux kernel, they are intercepted by iptables, and then there is an entire chain of IP table chains which are executed. So the first one, as you can see, if a packet comes in and it matches kube, it goes to kube services. Let me clear up this to make it a little bit more clear. You can actually do things like show me that kube services chain. That was, yeah. So as you can see, if you go through this entire list, I'll just pick out one for the demo. You can actually see that there are lines for every service you actually create. Yeah? So you see that if something connects to this cluster IP on port HTTPS, but there's also some on HTTP, as you can see, because every service has 443 and port 80. We'll target basically this chain. This, the target chain here, is another chain inside of Iptables. That will basically tell you if, so this line basically says, if somebody connects to this service IP address, yeah, okay, do what's in the next chain, or the chain we target. And if I take an example here, this is one of the names I copy pasted before, but you can actually see that, oh, this is cool. This is the one we actually scaled up. So you can actually see that if somebody connects to that cluster IP address, we basically hit this chain, and this chain is a little bit complex, but it basically says, you see the probability that this rule is hit. This is how kube services implement, that Iptables implement the load balancing of the service. Yeah, so it's not, it's cool, it's fast, but it's not the most, should I say, feature-rich way to do it. But actually, these random probabilities here basically tell you that if you hit the first rule, you're 2 out of 10 that this rule is hit. And so you can see that basically once you hit the last rule, you have 50% chance of hitting this rule or this rule. Very probability-like, but at the end of the day, the idea of this chain is to basically say that you have 1 chance out of 5 to hit one or the other target here. And if we basically check out that target, we can basically see that this contains finally the information that says, okay, if you hit and finally reach this rule, please destination net to this IP address port 80. Well, we made the bridge. So from a cluster IP, we go through all these chains to finally come here, which basically says, if you're getting up here, please forward the incoming connection to this IP address port 80. And this IP address is basically one of the IP addresses of the backend spots. So that's the entire concept. A little bit over time, but just to conclude this, this is how cluster IP works. So what about NodePort? So if you check this entire Iptables listing, you could basically also see that there is a chain called kube-node. And at this moment, it's empty for the very simple reason that we didn't define a NodePort. So let's see if we can modify our example. So let me create one. Okay, so let's see if we can basically, should use the correct name. Let's see if we can expose a part of the application by creating a service. Okay, so as you can see, there is a service. I added the type NodePort here. So pretty cool. It's there. If I do exit, let me just see if it is there because it was already there. Okay. So you see there is no higher port specified. Same idea, just type NodePort. So if we're going to apply this service definition, well, we should be able to actually see if we do kubectl get services in up demo that it has changed to NodePort. NodePort, as I said, exposes higher port numbers here. There's one for the HTTP and one for this. So that basically means if I would curl to local host here and to this port, it will give a 404 error, but that's for other reasons. You see that I have connectivity to the Nginx because it's based on host names that it gives this error. Okay, so that's the way to expose. Pretty simple. So if you check out the Iptables change right now, and let's see if I can find that back. You actually see that Iptables is already updated on every node, and that we basically added an Iptables rule saying that if somebody connects to this destination port, send it to the service with this crappy name. That service will basically show us which, this is a service which is basically in the kube services chain. That will basically list all the endpoints and finally all the, so it's by adding this type NodePort, sorry, we actually created additional rules that make sure that the IP addresses or the 0000 IP address on the host name is actually address translated correctly. I didn't try it, but if you do netstat -an, you should basically see here somewhere these higher port numbers spin up. Let's see. Yeah, it should. There would have been easy ways to do this, but if I'm not mistaken, can we find this port? You see, there is a listening socket on port 3145. So that means this is on the host. So if you do netstat on the host, you'll see that it's listening. So anyone at this moment that connects to this port can reach this application. And of course, the next step would be, if you don't like that, to implement network security policies or firewall rules that actually limit access to this service. I'll take a few minutes to answer some questions if there are. If not, I would like to thank you for attending. If you have suggestions about topics for next webinars, feel free to reach out. Otherwise, we have to choose them. So we'll be more happy if the community can choose which topics we address. And if you have any other things which keep on spinning in your mind about this subject, we're here to answer your questions. So thank you. If there are questions, feel free.
Thank you, Philippe.
No questions. I see some chats. In the chat, there are some. Okay, there were no questions. Okay. So I don't know if Jane answered already, but about the links, they will be sent out, and the YouTube version of this webinar is also available, but it might take a while because of some holidays and holidays, typically in the US. But they should be available. If not, reach out. Thanks, everyone. Have a great day. And okay, so and hope to see you soon somewhere in cyberspace or in real life. Thanks.